Section 1. Preface. If you've been following the generative recommendation wave, you've seen two worlds colliding. Recommender systems that have traditionally scaled by growing giant embedding tables, and LLMs that scale by growing compute-heavy networks operating over compact tokens. This paper is important because it shows a credible, launched path to bring those worlds together at industrial scale. It replaces billion-parameter embedding tables with compact semantic ID tokens, adapts an LLM to understand those tokens and user behavior, and then directly generates recommended items. It's not a toy setup. This is deployed on YouTube across long-form and shorts with live A/B gains and serious engineering detail around training, serving, and scaling. Section 2. Title and authors. Context in the field. PLUM Adapting Pre-trained Language Models for Industrial-Scale Generative Recommendations by Runing He, Lucas Helt, and colleagues at Google DeepMind and YouTube. Context-wise, this work extends prior semantic ID and generative retrieval efforts, like Tiger, but crucially moves from training from scratch to aligning a pre-trained LLM to the recommendation domain. It sits alongside recent foundation model efforts in Rexus and offers a concrete production recipe built on Gemini-style Mixture of Experts (MOE). Abstract. Key claims and results, rewritten for spoken explanation. The authors introduce PLUM, a three-stage framework. Convert each item, video, into a compact sequence of discrete tokens called semantic IDs, improved with multimodal content fusion, a behavior-aware contrastive signal, and a more coherent quantization hierarchy. Continue pre-training a base LLM to align these new tokens with language and user behavior sequences so the model understands what these IDs mean and how users consume them. Fine-tune the LLM for a generative retrieval objective. Given a user's context and history, the model directly generates the semantic IDs of likely next items. On the large-scale internal YouTube data, PLUM's generative retrieval beats a heavily tuned production baseline that relies on massive embedding tables. It scales effectively up to circa 900M activated parameters, MOE, converges faster than the baseline despite having a much larger dense network, and runs in production for billions of users. They also share learning curves and scaling laws, an ablation showing the SID improvements matter, and live A/B results that show additive value on top of existing systems. Introduction. Problem framing and motivation. Industrial recommenders have long depended on huge embedding tables for high cardinality IDs, super effective at memorization, but they crowd out model capacity and make it hard to benefit from deeper networks. LLMs, by contrast, push capacity into the network and rely on compact tokens. There's an emerging shift in recommendation toward LLM-like training and architectures, but off-the-shelf LLMs don't natively understand user interaction data or item corpora, and they can struggle to close the gap with mature baselines. Also, if you keep old ID embeddings, you inherit scaling bottlenecks. PLUM tackles both issues. Replace ID items with compact semantic IDs so the network, not the table, carries most of the capacity. Then align a pre-trained LLM to domain data, items, and user behaviors via continued pre-training. And finally, fine-tune it to auto-regressively generate items. The bet is that more compute in the network plus better tokenization yields higher sample efficiency, better scaling, and a path to production. Model, method, core approach, pre-training, architecture, objectives. Think of PLUM as a three-stage pipeline. 1. Semantic IDs, SID v2, the item tokenizer. Multimodal fusion. They fuse multiple content embeddings, e.g. title or text, thumbnails, vision, audio ASR, into a single dense representation via encoders and a projection, pragmatic and extensible to new modalities. Improved quantization hierarchy. Instead of uniform codebooks at each level, they use multi-resolution codebooks. Early levels have high capacity to carve out big semantic regions. Later levels use smaller codebooks to encode residual details. Progressive masking during training enforces a clean hierarchy, so early codes carry most semantics, later codes refine. Behavior-aware contrastive signal. They inject user co-occurrence signals into the SID training, encouraging items frequently watched together to quantize to closer codes without relying on dynamic CF embeddings. This keeps the quantizer stable while still reflecting user-perceived similarity. Why this matters? Better tokens reduce collisions, preserve semantics relevant to recommendation, and make the generative model's job easier. The contrastive objective is a clever way to bake behavioral structure into a static tokenizer. 2. Continued pre-training, CPT. Align the LLM to the new modality. Expand the LLM vocabulary to include SID tokens, then continue pre-training on a 50-50 mix of user behavior sequences and item metadata, titles, descriptions, ASR, channel, and synthetic variants. The goal is to ground SID tokens in natural language and model user behavioral patterns. They monitor both SID language modeling and standard text benchmarks to track any degradation. Why this matters? It bridges the domain gap. Off-the-shelf LLMs don't know these tokens or this user sequence distribution. CPT gives the model a working, generalizable representation before any task-specific fine-tuning. 3. Task-specific fine-tuning, SFT. Generative retrieval. Autoregressive objective. Given a prompt that interleaves a user's history as SID tokens plus feature tokens, current context, and other side features, text and numeric tokens, train the model to generate the next item's SID sequence. Training examples are weighted or sampled using a handcrafted reward proxy to prioritize clicks likely to reflect good user experience. Inference. Beam search produces multiple SID sequences, which are mapped back to videos. They report low SID hallucination, less than 5%, and high uniqueness in mapping. Why this matters? Generative retrieval avoids maintaining separate ANN indices or dot product constraints, enables end-to-end modeling of long-range dependencies and feature interactions, and directly targets the items users will click next. Experiments. Zero-shot transfer. What it's testing conceptually. Can an LLM, after CPT but before supervised fine-tuning, already use SID tokens in a meaningful way, e.g. generate next item SIDs from history or produce language conditioned on SIDs? Does mixing SIDs and text during CPT preserve general language ability while learning this new modality? Why the setup is interesting. Zero-shot ability indicates whether CPT truly aligns the new tokens with the model's existing knowledge, potentially reducing the data and time needed for fine-tuning. It also probes whether language modeling and SID modeling can coexist without catastrophic forgetting. What they found, and what's valid versus overstated. The authors report that after CPT, the model can generate next video SIDs from history and produce coherent text conditioned on SIDs. They also track standard text benchmarks to monitor degradation. However, they do not claim that zero-shot is sufficient for production-grade retrieval. They explicitly add a supervised fine-tuning stage and show large gains. How this should influence real-world system design. Treat CPT as capability seeding. It gives the model the language of items and behaviors. Don't skip SFT if you care about precision. But CPT can reduce SFD data needs, speed up convergence, and enable multitask reuse of a single domain-aligned checkpoint. Experiments. Few-shot learning. What it's testing conceptually. Does the CPT-aligned model exhibit in-context learning with the new SID modality? Can it follow simple text instructions that involve SIDs and produce appropriate natural language completions? Why the setup is interesting or non-obvious. In-context behaviors and recommendation settings are less studied than in pure NLP. Demonstrating that an LLM can reason over SIDs in few-shot prompts suggests future user-facing or operator-facing interfaces that blend language and IDs. What they found, and what's valid versus overstated. Qualitative examples. The LLM initialized model after CPT produces coherent text following few-shot prompts involving SIDs. A randomly initialized counterpart does not. This supports the claim that general-purpose LLM pre-training helps ICL survive CPT. It's anecdotal and not a retrieval metric, treated as evidence of capability, not performance. Design implications. Keep natural language tokens in the CPT mix. It preserves ICL and makes downstream prompts more flexible. For interactive tools, you can mix human-readable text and SID tokens in prompts without retraining a specialized interface model. Experiments. Representation learning. What it's testing conceptually. Do the SID v2 improvements produce better item tokens for generative retrieval? 2 key qualities: uniqueness, 1 SID per item with few collisions, and usefulness. Do better SIDs translate into higher recall in downstream generation? Why the setup is interesting or non